In this video, I want to build on what you learned in the 3 blue, 1 brown video about determinants. If you haven't watched that video yet, please watch that before this, otherwise a lot of what I'm saying won't make sense. I'm not going to repeat everything that was in that video for any number of reasons, including that video has amazing animations of what's actually going on, and so I highly recommend it. Watch it if you haven't already, but I do want to recap and highlight some important points. My main goal in this video is to take what happened in that video and translate it to higher dimensions, dimensions bigger than 3, so that we can understand how determinants apply there and what they're telling us. So just to recall a few things about determinants, some of which is in that video, one way to think about linear transformations from Rn to Rn, that is to say, linear transformations that start in Rn and end in the same dimensional space, right? Lots of transformations don't do that. But when we're working with the same space, we can think of them as stretching that space out or contracting that space, or maybe rotating that space or reflecting that space, and some combination of these things, all while keeping the origin fixed. This is a special type of function where you're not bending any lines. And one of the main points of the 3 blue, 1 brown video was that when you have this situation, you're changing volumes, in this case I'm thinking n volumes, which I'll talk about more about, by the same multiple. So let's look at an example to see what I mean by that. So we'll start in R2. So in R2, I'm going to start with our standard basis. So we have the vector 1, 0 in green and the vector 0, 1 in blue. And I'm going to apply a linear transformation that is going to leave that blue vector fixed, but send the vector 1, 0 to the vector 2, 2. So if I define where a linear transformation sends a basis, it tells you where it sends all points. So hopefully it makes sense how I'm defining this transformation. I'm trying to do it visually. And one way of thinking about this transformation is that it takes this unit unit square. I'm already thinking into higher dimensions. And what it's going to do is it's going to send it, when I move the green vector like this and I leave the blue vector fixed, it's going to send the unit cube to this parallelogram. And if you look at this, what you realize, you can kind of work this out. You may not have thought about area of parallelograms in a long time, but the base length, if we're thinking of the vertical side as the base, is 1, and then the height is 2. And so this has an area of 2. So I've taken something with area 1, and I've mapped it to something with area 2. But it turns out, if I look at some other region, so for instance, if I start with the unit, let's move here, the unit circle and the unit disk, I'm filling it in, and I've left the basis vectors here because they'll be useful. I'm going to zoom out a little bit. If I start with the unit circle and I ask, well, what happens when I leave the blue vector fixed, but I move the green vector up, same linear transformation, what you end up getting is that this turns into an ellipse that I've drawn in purple. And the area of this ellipse is twice the area of the unit circle. So I've also doubled this area. And so when I say that a linear transformation will change all n volumes by the same amount, what I'm saying is, look, I'm in R2, and so area is what I mean by n volume. Two-dimensional volume is area. And this linear transformation doubles all areas. Let's quickly move to R3. I'm not going to dwell too long on this. So in R3, we can do a similar sort of thing. We can start with our standard basis, and we can apply a linear transformation that takes our first standard basis vector to here. And I'm drawing them in the same color so you can kind of follow where they go, right? So the blue vector goes to the new blue vector, the green vector goes to the new green vector, and the orange vector goes to the new orange vector. So this linear transformation is going to take the unit cube that I've drawn right here, and it's going to map it to this region. And let's clean this up a little bit because it starts overlapping. Let's see just what it maps to. right? So we end up with this sort of thing, this parallel pipette. And in this case, this linear transformation is mapping. It's harder to see because it's a parallel pipette, and we're just looking at a Desmos graph of it, but it's actually tripled the volume of this thing. And it's also switched its orientation, which I'm not going to dive into. The 3 blue 1 brown video talks about this. It's changed the orientation of this region as well. And so you might ask, well, what happens to a different region? And let's do the same sort of thing. Let's start with our basis, but instead of looking at the unit cube, let's look at the unit sphere. And I knew this was going to happen. So as soon as I draw the sphere, the basis is gone. Or I didn't know. I figured this would probably happen. That's fine. Where does this unit sphere get sent? Well, it gets mapped to, and let's change the color so we can really see here. The unit sphere gets mapped to this ellipsoid. Right, so I go from this thing, and then I apply the linear transformation, and I end up with this thing. And it's believable looking at this that, and this is true, that this ellipsoid has 3 times the volume of the unit sphere. And also, its orientation is switched. So linear transformations in R3 are taking volumes and sending them to the same multiple of that volume. There's an important note here, which is that when I'm talking about this, I'm talking about the highest dimensional volume. And let's go back to R2 to see this. This linear transformation that I looked at, we don't even need the areas anymore. It doubles all areas, but it doesn't change all lengths by the same amount, which is really obvious just from its definition, right? It didn't even touch the blue vector. It left it there, but it made the green vector longer, right? The green vector went from length 1 to length 2 root 2, almost 3. So we're only talking about the highest dimension, like the corresponding dimension, right? If we're working in R3, we're saying a linear transformation from R3 to R3 will send all 3-dimensional volume, which is just traditional volume, to the same multiple of its volume, but it won't do the same for an area or a length. Okay, so how does this all tie into the determinant? And this is kind of the punchline of the 3 blue 1 brown video, which again, please watch if you haven't already. I can't say that enough because the animations really give you a good sense of what's going on in R2 and R3, is that the determinant tells us this multiple. So the determinant of a linear transformation tells us this multiple, and it's negative if orientation is switched. So switching orientation corresponds to a reflection. And so if you have a single reflection, that's going to switch orientation. And so back to our examples, this linear transformation, defined by leaving the blue vector in place and sending the green vector to this longer vector, this doubled all areas and doesn't change their orientation, so it has determinant 2. And then in 3 dimensions, when we mapped our standard basis to these 3 vectors, we tripled all volumes, but also switched the orientation. So this linear transformation, the matrix corresponding to it, or the transformation, has determinant -3. Okay, so what happens when we go to higher dimensions? That's kind of the main point of this video, right? I wanted to recap that and show a little bit. But one of the main points is what happens in higher dimensions. What do we mean by volume in higher dimensions? So how do we talk about n volume or n area, whatever you want to call it, n-dimensional measure of space? It's actually not too bad because the area, an area of 1, so that's 2-dimensional, is the area of the unit square. And the unit square is just all the points with x and y between 1. And once you decide that that's the area of the unit square, all other areas are essentially forced if you want area to have a nice properties. And then a volume of 1 is the volume of the unit cube. And the unit cube is just all points whose x, y, and z values are between 0 and 1. And just to look at this picture, the picture in Desmos isn't great. It just because of somehow how it graphs it. But this is a unit cube, right? The side lengths are all 1. And if you look at these axes, you can convince yourself, it's kind of hard to see the numbers, but that this consists of all triples where x, y, and z are all numbers between 0 and 1. So once we have these two things down, I think it's pretty straightforward for what it should mean to have an n volume of 1. So an n volume of 1 is the n volume of the unit n cube. And the unit n cube is just, well, we have n variables, so x1 is going to be between 0 and 1. x2 is going to be between 0 and 1, all the way up to xn is going to have to be between 0 and 1. And so that's what an n volume of 1 is. And similar to in 2 and 3 dimensions, once you decide that that volume has 1 and you want volume to have some sort of nice properties, right? That if you chop a region into pieces or if you shrink in one dimension, it does what you'd want it to, then that forces all of your other volumes. So volume makes sense in higher dimensional space. And the determinant will tell us the same thing. Again, the determinant will tell us the multiple that is applied to all regions in terms of their n volume. And if orientation is switched, because there's a notion of orientation in these higher dimensions as well, which is harder to visualize, but certainly believable, then we'll get a negative on our determinant. So the determinant tells us the same thing in all dimensions, but one dimension that we skip a lot in this class is one-dimensional, and we skip it for a reason, because it's often a little too simple, a little too trivial, and there's not a whole lot to say, right? It's kind of the first thing you learn in algebra. But I think it's really useful in thinking about the determinant to understand what the determinant is in one dimension. The determinant in one dimension is slope. Like literally one of the first things you learned about in algebra. Whenever you first saw algebra and saw graphing, you learn about linear functions, you learn about slope. One-dimensional determinants are slope, and so another way to think about n-dimensional determinants is n-dimensional determinants generalize slope. Right, so what I'm saying here is that, your basic linear function y equals 3x, if you plug in, for instance, the interval 1, 3, and you triple everything, you take something of length 2 and you send it to something of length 6, right? You triple all lengths. And so the slope of your traditional linear function from algebra 1 is telling you how much lengths you're multiplied by. And determinants are doing the same thing for linear transformations in higher dimensions. The whole orientation thing also makes sense, right? Y, or I'm about to say y equals minus 2x. What does it do to this? Well, it takes 1, 3 to minus 2, minus 6. And so it's taken a length 2 thing to a length 4 thing, but it's written it backwards, right? These are in the wrong order. It's switched the order of things. It's changed orientation. So the determinant really is this generalization of slope. Slope tells us how much does a linear function multiply lengths by, because it changes all lengths by the same amount. That's the important property of it. And in higher dimensions, if we're going from the same dimension to the same dimension, a linear function changes all n volumes by the same multiple and maybe switches orientation, and that's what the determinant tells us. All right, so why is this useful? Why is it useful beyond 3 dimensions? Hopefully you've been convinced by the 3 blue 1 brown video and my brief recap and talking here that, all right, in n equals 2 and n equals 3, totally reasonable to think about how volumes and areas are changed. There are lots of answers to this, but one that you may have already seen, or a lot of you likely will see, is in Calculus 3. Where we're dealing with, for instance, some integral, double integral in x and y, and we want to change variables. Maybe we want to go, instead of dx dy to d theta or dr d theta, we want to go to polar coordinates. What we need to do is we need to figure out how much this transformation is changing areas by. And to do that, we use determinants. And so as you get to higher dimensions, calculus, here we use determinants. As you get to higher dimensions, it makes a ton of sense to take triple, quadruple integrals of over however many variables you want, because you're not always talking about space, right? Your variables can represent other things. And when you want to change variables, which is very useful, you use determinants, what's known as the Jacobian, to figure out how much that change of variables has changed your n volume. There's another situation that actually applies to what we're talking about more directly, which is that determinants can be useful even when it's not obvious that you're talking about volume. So a determinant of 0, the 3 blue 1 brown video talks about this in 2 and 3 dimensions, means that you're taking a region that has volume and squishing it to a region that doesn't, or in other words, you're mapping a lot of points to the same place. It means that the linear transformation is not invertible. So here the determinant tells us something that is not obviously initially about volume, whether or not the transformation is invertible, but ultimately it is, right? It's a question of whether it's squishing points down to one place. And we'll see when we talk about eigenvalues, which is coming up soon, that the determinant shows up again in a situation that's not clearly having anything to do with volume. So it makes sense. It's a generalization of slope. It tells us a natural thing, and then it starts to show up over and over again. And so we say, this is a useful thing. We should define it. We should study it. So how are we going to find the determinant of a matrix? That is the determinant of the corresponding linear transformation. There's going to be a few steps behind our logic, and I'm not going to do this in this video. Right now, what I want to do is I want to outline what we're going to do so that you have a picture of how are we going to find determinants. The first thing is to observe this very useful property that, again, is in the 3 blue 1 brown video, that if we take the determinant of a product, if we think about this in terms of linear transformations, we're saying, well, we first hit it with B because it's all backwards, right? And we change the volume by some amount, some multiple, and then we hit it with A and we change it by that multiple. If you think about what that does, it changes it by the product of those multiples, right? So if B cuts your volumes in half and then A triples your volumes, the end result is that you've multiplied your volumes by 3 halves. And so this is going to be our first observation, that we can calculate determinants by splitting matrices into products. And Then what we'll see is that the elementary matrices, the matrices corresponding to elementary row operations, have nice determinants in the sense that we can find them easily. And finally, one thing we've used, for instance, when we were finding inverses of matrices, is that every invertible matrix is the product of elementary matrices, right? This is what allowed us to find the inverse. We just applied a bunch of elementary row operations until we got the identity. And so our plan is going to be figure out how to find the determinants of elementary matrices, which will be really easy. If not even like, we won't have to do any work. Once we know what they are, they're very simple. And then all we have to do is try to write our matrix as a product of elementary matrices, which we know how to do, right? That's just saying apply row operations until we get the identity. And either at the end of that whole process, we'll know the determinant of our matrix because we've written it as a product, or we'll have found out that in fact our matrix is not invertible and it has determinant 0. So that's our plan going forward.